Hi there. So we are going to do like a quick intro to sampling distributions together. So I want to take a minute to consider this situation here where we have the heights of young women. So the heights of young women vary approximately according to a normal distribution with mean 64.5 inches and standard deviation 2.5 inches. So that means that if I were to take like the population of young women, I could draw a normal distribution. Oh no, my pen is not lined up. I could draw a normal distribution and label the mean 64.5 inches, and then go out to 1, 2, and 3 standard deviations from the mean. This follows the 68, 95, 99.7 rule, blah, 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 all that stuff that we know about normal distributions, right? So now I want to take a minute and see what would happen if I use the calculator to simulate taking an SRS of young women. So I'm on step 1 here. I can use the function math and then scroll over to PRB, and then on my calculator it's option 6, rand norm. Rand norm is like random normal. That means you're asking the calculator to pick a value from a normal distribution randomly. So we're telling the calculator we want our normal distribution to have the same mean as the population. So 64.5 inches, standard deviation 2.5 inches, that's what our population is, right? And I want you to randomly pick me 100 women and give me those heights. So if I hit paste, this is what it brings me out to the home screen. Now what I can do is I can store all of those values into L1. So before I hit enter, I'm going to hit STO arrow, that's this button at the bottom here, and then second L1. Hit enter. It might take a minute, but you can see now it's given me all of these heights that are randomly chosen values that fall within that normal distribution. So if I go into stat edit, and don't worry about what's in the rest of these, but in L1 it has now stored all these values, and if I scroll down to the bottom you can see that there's 100 values here, right? So what we want to do is we want to look and kind of compare this sample to the population. So if I look at the sample, I want to make a histogram of everything that I have in L1. So that's sample. I'm going to zoom 9, and that's what that looks like. So the shape is kind of, I don't know, it's actually kind of like left skewed, right? But if I were to find the mean, median, and standard deviation in like in question number 3 here, I'm going to go second quit, stat, calc, one variable statistics of L1, and I want to get this out of here because I don't want it to be weighted. So I just want the mean, median, all that good stuff. So this tells me here that from my sample, the mean of the sample is 64.734 inches. My standard deviation from my sample is 2.509 inches. My median, if I scroll down a little bit, oops, is 65.105 inches, right? And that kind of lines up to what the population should be. So I can kind of see that the mean of my sample is very close to the mean of the population, 64.5 inches. The standard deviation of my sample is really close to the standard deviation of the population, 2.5 inches. And if it's normally distributed, if the population is normally distributed, then the median is also going to be close to 64.5 inches, and that's what we have here. My median is 65 inches, so it's a little higher. So in question number 4, it says approximately how many heights should be within 1, 2, and 3 standard deviations of the mean. Well, if my sample is normally distributed, it should follow the 68, 95, 99.7 rule. Now my pen is really not lined up well here, so I'm going to do the best I can. But that tells me that within 1 standard deviation from the mean, I should be able to take 64.734 and add 2.509. So I get 67.243, and I can take that same 64.734 and subtract 2.509, so 62.225. So within 1 standard deviation of the mean, that should be the range of my heights. Now, if I subtract another 2.509, I'm at 59.716 inches, and then if I take that 67.243 and add another 2.509, I get 69.752. And so right now I'm just calculating the range of heights that I should have within 1, 2, and 3 standard deviations of the mean. So this goes up to 72.261, and if I do 59.716 minus 2.509, so this is 57.207. All right, so now if I go back to my sample that's in L1, right? Remember, I can sort L1 from biggest value to smallest value. Remember we did this in chapter 2 when we looked at normal distribution. So I went to the home screen. Let me do that one more time. I went to the home screen. I did second list. No, I'm sorry. I did stat. Don't hit second. So just stat and then sort A for sort ascending. And I want to sort L1. It just says done. So if I go back into stat edit, now this list is sorted, and I can it's easier to kind of check to see how many values are outside of the range, and then kind of subtract from 100. Remember, there's 100 total in my sample here. So my smallest value should go to 57.207. It doesn't go below that, right? My smallest height is 58.101 inches. My tallest young woman is 70.839. So I don't have anyone outside of 3 standard deviations. So in other words, I have 100% of my women within 3 standard deviations of the mean. Now let's check 2 standard deviations. So it only goes up to 69.752 inches. So there's 1, 2, 3 women that are taller than that, right? And then if I go to the bottom, it should go down to 59.716. So there's 1, 2, but then this third one is taller than 59.716. So, right, that minimum there. So it's really just these 2 at the bottom. So it was the 3 at the top plus the 2 at the bottom. So we get rid of those 5 women. And then the rest of the 95, because there's 100 total women, so 95% of the women are within 2 standard deviations of the mean. Now let's look in 1 standard deviation. So we need to go, our minimum is 62.225. So let's count how many heights were below that. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Nope, sorry, not 18, because that 18th, right, that 62.369, that 18th is within the range. So really there's 17, I'm going to write this down, so 17 women below this minimum here for 1 standard deviation, right? So it's below 62.225 inches. There's 17 women. And then let's see, let's go to our top range. We want how many women cut off above 67.243 inches. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14, I think, right? Because then this last one here, this 67.22 inches, that's underneath that kind of cutoff there. So I had 17 on the bottom, 14 on the top. That's a total of 31. So 100 minus 31 is 69. So this tells me that even though when I looked at the graph, at the histogram, it almost kind of looked a little skewed. Even though it looks almost a little skewed, it still is going to have this 68, 95, 99.7. It's pretty close to those percentages. So even though this looks a little skewed, this sample is very close to normally distributed. So in other words, my sample that I selected is very close to the same shape, center spread, et cetera, as the population, which is what I should expect, right? Now, let me very quickly, I'm not going to go through this whole thing again, but if I go in and I cleared out L2, if I basically do this whole thing again, so I'm going to select, I'm going to go to Math, PRB, Random Normal, and I'm going to select another 100 women randomly from this normal population, and now I'm going to store them into L2, okay? So I have another 100 women that I have now stored into L2. So they were randomly selected, or I should say it was simulated that we randomly selected them using the calculator. Now, if I go in and I want to just quickly look, what does that histogram look like? So I'm just going to make a graph of L2. Look, that's much more symmetric looking. And if I stat calc one variable statistic, now L2, so I'm going to find the mean, median, mode, standard deviation. Look, my X bar, my mean is 64.271. So it's pretty close to 64.5. My standard deviation, 2.658, close to 2.5. My median, 64.335, close to what it should be. It should be 64.5 inches, right? So it's pretty close to that. And if I were to go through and create another table like this, I will bet you that my percentages are going to be, again, pretty close to the 68, 95, 99.7 rule. So again, this is just a quick reminder that when we have a population and we take a simple random sample, the sample should have very similar properties. So what you're going to do for me today is you're going to essentially follow the directions that I posted on Schoology, but you're essentially going to repeat this process. You're going to come up with a bunch of your own random samples, and you're going to look at them, and you're going to, at least for one of them in particular, you're going to check, does your sample follow the 68, 95, 99.7 rule? And so you can kind of hopefully see that all of these samples are representative of the mean. And then what you're going to do is you're going to repeat this process a whole bunch of times. You don't have to check the 68, 95, 99.7 rule every time. That's time consuming. But you're going to use the calculator to simulate taking an SRS of 100 women several times, and you're going to tell me the mean and the standard deviation from each of these samples. And then we're going to take all of those means and standard deviation. So everyone's going to select a bunch of samples. So we might have 70, 80, 90 samples, and the mean and the standard deviation from each of those. And we're going to see when we kind of compile all of those samples, we're going to see what kind of happens. And when we compile all those samples, that's what we call a sampling distribution.